Okay, good morning. Can you hear me? Okay, great, thanks. First, I would like to thank Klaus and Moritz invited me to give this talk. So, additional to the title which appeared in the I add one more items called 2.5D quantification and 3D statistical shape modeling of dysplastic hip. So, basically, the contents of my talk contains two parts. First, I will talk about evaluation of a 2.5D quantification of femoral head coverage in normal control subjects and patients with hip dysplasia. And then this actually motivated me to talk about why you need to do statistical shape modeling in order to get a more comprehensive understanding of the hip dysplasia. I think the motivation is the morphology of the hip joint and its relationship with hip disease is not well understood. I think you are the expert. So in clinical practice, a wide spectrum of hip joint configuration exists, and combinations of different deformities are often observed. For example, hip dysplasia is characterized by insufficient femoral head coverage. So both 2D and 3D method has been introduced to quantify femoral head coverage. I think 2D method with the AP X-ray is a standard and widely used, but only provide the indirect measurement of the femoral head coverage. 3D measurement is patient-specific and accurate, but there's a concern on radiation and cost, and also for postoperative usually is not available. So with I think several years ago, together with Moritz, we introduced this hip to norm. Basically, this method we claim it is 2.5D because the femoral head coverage, which we can do a 2D, 3D construction of the acetabulum rim and femoral head, and then do a simulated cranial caudal projection, and then use the simulated view to calculate the femoral head coverage. So it's not purely 2D, actually it's also not 3D, so that's why we label it as 2.5D. So in order to evaluate the application of this method for dysplastic hip, we collected two groups of data. In the control group, we have 42 hips, which is no morphological abnormalities. And in the patient group, we have diagnosed clinically as hip dysplasia. Basically, the LC angle is smaller than 10 degrees, and also some have regional symptom. There we have 40 hips. Instead of using X-ray, like in the clinical routine, here we use digitally reconstructed radiograph from the CT. The reason why we use it is because this allows us to control exactly the pelvic orientation in a simulated environment, such we can investigate the influence of the pelvic tilt on the 2.5D measurement. So here's typical examples. So it's a neutral position, and this is the simulated X-ray, and this backward and forward, and this is the typically when you get such a simulated DRS. The ground truth is a 3D measurement, which is introduced by my group based on CT segmented model. And as you can see, we actually have exactly a natural shape of the dysplastic femoral head, and then we can calculate the upper femoral head part, which the ratio between the covered and the complete upper part, which is regarded as the measurement of the femoral head coverage. So here shows our evaluation results. As you can see, here shows the 3D measurement, this is 2.5D measurement. Basically, both measurements can clearly separate the control group from the patient group. And with 3D measurement provide slightly higher accuracy, but still we use 2.5D. Actually, you can differentiate with certain threshold. We also measured the inter-observer reliability and intra-observer reproducibility of a 2.5D measurement, use the inter-class correlation. So you can see the ICC, here shows the ICC measurement. So basically we can say both the inter-observer reliability and the intra-observer reproducibility of the 2.5D measurement are very good. We also compared the 2.5D measurement, taking the 3D measurement as the ground truth, And here shows the linear correlation coefficient, and also measure the bias and precision. As you can see, very strong correlation between 2.5D and 3D measurement are found. And the last, we also investigate the inference of the pelvic tilt on the 2.5D measurement. So the range we're taking is from 10 degree to minus 30 degree, which actually the value taken from this paper. As you can see, since the hip to norm have to the method to automatically correct the pelvic male orientation, so basically the inference is there is certain inference but quite small. So this is only actually just to evaluate dysplastic hip with one parameter, it's a femoral head coverage. And does this tell you the complete story about the morphology? So this actually motivates us to go to understand better with statistical shape modeling. So if you want to have a more comprehensive morphological comparison between normal control subject and with patient with dysplasia, probably with statistical shape modeling is a better technology. So what is statistical shape modeling for those who doesn't know it? So it's a common technology used to study the morphological variations and the association with different characteristics. So basically, as you can see here, the statistical shape model we generate from this technique capture the mean model, the average model from this population, as well as the main modes of the variation. Here shows just one of the mode. So in a nutshell, statistical shape modeling, basically you start with a collection of population data, you through a step called correspondence building, and finally you generate the statistical shape models, as you can see here. When you have this raw data, it's just a random jump. But after the correspondence building, you get quite homogeneous variations. So how to build the correspondence? Usually this is formulated as image registration problem, although here I did not use the pelvis, but use head. For example, we manually annotated two landmarks in the nose tip and the root of the nose. So this is another head skull, which is yellow. So by image registration, I should find exactly same 2 points, as you can see by these animations. So this means with this algorithm now, you found one point by point or voxel by voxel correspondence. So this allows us to build the statistical shape modeling. So what are the current state of art? So I only found 2 works which apply statistical shape modeling for hip joint. Both focus on one single structure, which is the proximal femur. So one is to investigate the proximal femur shape deformity and LPCD, and second actually is investigate the cam deformity. So in this work, actually we build a compound model by considering not only one single structure, but both femur and acetabulum simultaneously. So here shows the results. So basically this first shows the mean model construct from these 2 groups. This is the control group, so the normal subject. Probably you can say the coverage, I think is normal, according to your experience. And here you see this dysplastic hip, the mean model. I think it also apparently shows this insufficient coverage. And this is variation. So again, left side, this side is a control group. This is this dysplastic hip group. So it's too small, but later I will show you the animation. So that's the mean model, and this is the minus 3 times standard deviation first mode, plus 3 times standard first mode, and second mode, and third mode. And again, same arranged here with the dysplastic hip. So you could say, I think in this, no matter how to change it, more or less, this is all in the normal range for the femoral head coverage. While this one apparently shows the insufficient coverage. If we go a little bit deeper, we can compare one by one. So this is along the first mode. So this is the control group. So with transparency, you can easily identify how much is covered, the femoral head covered by the acetabulum. And here you can say in the dysplastic hip group, not only have insufficient coverage, but also actually the head is a little bit sleepy from one location to another location. And then you move on to second mode. So again, you can compare this control group with this dysplastic group. The very funny thing is, in this second mode, I think this is the left side, when he goes straight up, and this one actually go in. So I don't know whether it's linking to the first talk, which is abductor stuff. I have no idea. Probably you can do an interpretation. And if you then move on to the third, and now change to another side. The second Eiger mode and third Eiger mode shows more or less same variation, but actually different side. One left side, one right side. As you can see again here, but the control group actually shows similar behavior, but actually all is normal. So to conclude, in this presentation, we evaluated the 2.5D quantification of the family head coverage in normal control subjects and patients with hip dysplasia. This motivated us to construct statistical shape models of dysplastic hips and in comparison with the normal hips. So besides what I showed here to describe morphology difference between normal control subject and the dysplastic hips, I think we plan to use this constructed statistical shape model of the dysplastic hips in our single image-based 2D/3D reconstruction program, such that we can measure the dysplastic hip orientation, which at this moment is not available in the hip to norm program. So beyond that, should we only consider in bony structure, or should we also consider in muscle? I think you can see this is definitely not this is actually not the dysplastic hip group, but actually from total hip osteoporosis group. So you could definitely link in the motion or the morphological change of the bony structure with the change of the size of the muscle. So does this actually should be considered? So this I leave to you to have a thought. Okay, thank you for your attention.